Well, this is the third and final presentation on alkenes and the polar reactions that they can undergo. So just to kind of finish up discussion of alkenes and put it in the context of reactions we've already considered, we have looked at in the last two presentations, really, in a nutshell, the attack of electrophiles, whether it be protons, bromine and Br2, boron and BH3, the attack of these electrophilic sites with the pi electrons. That has, in the beginning, been set apart or set different from what we did with alkyl halides. In the case of an alkyl halide, we took a nucleophile and we attacked the alkyl halide. So in the transition from where we've been, alkyl halides with nucleophiles, the arrows were flipped. The functional group, which was attacked in your SN2, SN1, E2, E1 reactions, where the nucleophile could attack the carbon connected to the chlorine either as this comes off or after it comes off, SN2 or SN1, or it could attack the beta protons. Circling the CX, you can attack these beta protons on carbons next to the carbon Cl bond or carbon leaving group that's here, whether it be bromine, chlorine, or some other leaving group. Well, the beta protons could also be attacked, and that was at the same time this comes off, E2, or after this chlorine comes off, E1. But the difference, significant difference between alkyl halides and how they react and alkenes and how they react is in the way we understand the polar reactions. This was being attacked. This is attacking an electrophile. And we said this electrophile can be H and HCl, B and BH3, bromine and Br2. There are a lot of different electrophiles this alkene could attack. These are polar reactions. Polar reactions of alkenes and alkyl halides. I'd like to finish our discussion of the alkene reactions by looking at not polar reactions, but reduction-oxidation reactions. So looking at the addition of, usually when we say reduction, we usually mean addition of, not always, but oftentimes, hydrogens, and in oxidation addition, just talking about not a pathway, but just as far as numbers of hydrogens, they go up, and addition of oxygen. In general, the number of oxygens to the structure goes up. Now, I'm not talking about addition reactions in the sense of A plus A gives B, or A plus A gives B. Just saying that the number of hydrogens usually goes up with reduction, and in oxidation, the number of oxygens goes up. You can also have reactions where we take away oxygens, that would be reduction, or we take away hydrogens, that would be oxidation. So let's look at some reduction-oxidation reactions of alkenes and we'll be done. This again is the third video on alkenes. So in this reaction we're going to add hydrogens. Now it's hard to just simply take and add hydrogen gas to an alkene and hope it reacts. You have to do a little bit more than that. You have to add a metal, palladium, platinum, that can activate the hydrogen. It can break the strong, covalently strong hydrogen-hydrogen bond. So we do that by taking hydrogens that's here in white, and these are the hydrogen gas molecules. The hydrogens in white here are tethered to the metal surface. They have broken their hydrogen-hydrogen bond and made hydrogen palladium, hydrogen platinum, hydrogen nickel, rhodium, whatever that metal surface is. This is our metal. We're representing by this, I guess, this plate here. That's our metal. So it's a heterogeneous reaction where the hydrogen has already pacified the metal surface, they'll say, or has reacted with the metal surface. These are now a much more reactive form of hydrogen. The alkene, in the same way, binds to the metal surface. So this is our alkene here, and our alkene is coming in on the surface. These in black are the carbons, and they make a bond to the metal surface. We break the carbon-carbon pi bond and we make carbon-metal bonds. And now insertion starts to occur. Syn addition of the hydrogens, meaning on the same side. Hydrogens start to add in off the same side of the face of the pi bond. So up here, we used a face that was more accessible. This face was less accessible. This top face, the bottom face, away from this this tertiary carbon having two methyl groups off of it, we use the opposite face to approach the metal, the favored face. And of course across that face then we add the hydrogens. So we don't add them from the top because of this blocking of the two methyl groups, we add it from the bottom. So one face of this particular alkene is more accessible than the other. So that's our syn addition of hydrogen to an alkene, sometimes having to consider which face is more accessible. Of course, if we had something symmetric like this, either face can be added across. We can show the hydrogens that are coming in as being wedge, the ones that are coming on. And these is dash dash, but it doesn't matter. Both faces of this alkene are equally accessible. Here they were not. Alright, that's our discussion of reduction, just addition of hydrogen across an alkene. This is called hydrogenation. We have to have a metal catalyst to catalyze this reaction. Now let's look at oxidation. Partial and in a sense full. We're going to take our first example of oxidation. Again, we're just kind of adding hydrogens, or sorry, adding oxygens. Just typically what you see with oxidation, not all of them, but very common to have an oxidizing agent just simply add an oxygen to the hydrocarbon structure. Now, epoxidation, we simply have some sort of peroxy acid where we have a linkage, it's a peroxy linkage, within a carboxylic acid group. That can be written in text form then as some R group, whatever it might be, alkyl, benzene ring, some R group, with the carbon in the carbonyl, and between the carbonyl and the H, two oxygens, not just one. So this is called a peroxy acid. You see CO3H, that's a peroxy acid, and we're going to get epoxidation of an alkene. So the alkene reacts with the peroxy acid to make an epoxide. Epoxides have a CCO three-membered ring. That's an epoxide. We make one with these peroxy acids, and we make as a byproduct carboxylic acid. Now the methyl groups of course have to be on the same side because the oxygen has to be on the same side of the ring, the face. So the oxygen could have come across the top face, so wedge, but it also could have come across the bottom face where the methyl groups are pointing up. The methyl groups are pointing up and the oxygen is down. But of course, these two are exactly the same. I can flip this over and lay it right back on top of this structure. So we just have two ways to get to our epoxide product. So epoxidation of alkenes, remember, we have to look for this peroxy acid. If we see that, we think, oh, we make an epoxide, breaking the pi bond and making two carbon-oxygen sigma bonds to an oxygen to make an epoxide. Excuse me. Drink my cup here. Hey, this is the last reaction consider for alkenes oxidation of greater nature, where we're going to break not just the pi, but also the sigma in the double bond. So we basically pull those two carbons apart and replace both the pi and the sigma. The bond that's harder to break is the sigma. So epoxidation, we keep the sigma bond, and we only break the pi bond. But in ozonolysis or oxidation using, sorry about that, ozonolysis, we have the power outage here. Sorry for that 3-second of darkness. So we can pull away if we have ozonolysis. Ozone is a very reactive oxidizing agent. You actually usually make it in solution. You don't buy bottles of ozone. And what we do is we make, and the mechanism's not discussed in this presentation, but you make an malozanide. Let's get through this thing. Hopefully the power stays on. Make a malozanide, and it breaks apart the C. It makes a ring structure involving these two carbons and the three oxygens, and it ends up breaking both the sigma and the pi bond. To draw the product quickly, we can just cut the sigma and the pi bond, back these two away, put oxygens in place of the two carbons, so these are now bonded to oxygens, and then consider the reducing or oxidizing workup. This is a workup of the ozonolysis products. If the workup is reductive, where we have a metal that's in a reduced state, a +0 state, that's a reductive workup, we can have maintaining of the CH bonds off of carbons in this double bond. So there's two hydrogens here. We're going to keep them if we're in reductive workup. If, however, in ozonolysis we follow up with oxidative workup, where we have peroxide instead of zinc with water or dimethyl sulfide, this is also a reductive workup. If we have oxidative workup, you just need to recognize that, the carbon-hydrogen bonds involving carbons in that original double bond go to OH groups. So we still split, we still put oxygens in their place, but instead of drawing this as our product, where we have two H's there, this goes to two OH's, these are transformed into OH groups, and if we have two of them, if two OH is off the same carbon, this is carbonic acid, it breaks apart to CO2 plus water. This is carbonic acid, it gives us in the end CO2 plus water. So if we have two off the same carbon, and you have oxidation and oxidative workup after ozonolysis, you make our product over here, just backing away the carbon. We put an O on it, O on this carbon, and we're done. But on this side, we make originally carbonic acid, which goes into CO2 and water if in room temperature and pressure that system's allowed to sit. So I have those summarized down here. If a CH bond in oxidative workup, we change it to a COH. If we have two hydrogens, then we replace when we replace that group, or we make not carbonic acid, but CO2. Well, that's it as far as ozonolysis and reductive workup. Keep those H's on. Oxidative workup, take those H's off and put OH's in their place. Let's go ahead and just quickly summarize in the three videos where we've been. We've looked at polar reactions of alkenes. So all of these here are the polar reactions. From HX, H plus with alcohol or water, Br, Br2 with alcohol or water, hydroboration, oxidation. These are all the polar reactions. And I've made some notes. If it's an acid, a Bronsted acid, go Markovnikov. There's going to be a carbocation, and there's no stereoselectivity in the second step as far as how to attack the carbocation. With Br2 or Br2 in water or alcohol, we have Markovnikov addition, but we have stereoselectivity to anti-addition of the X two of them, or the X and OR. So either XX added Markovnikov anti, or XOR added Markovnikov in an anti-stereochemistry. We do the same sort of notes for BH3 and our hydroboration oxidation. It's anti-Markovnikov addition of water, and it's syn addition, stereochemically. Regiochemical note, stereochemical note. Now, I've gone on around the circle here with other notes for reduction. It's a syn addition, peroxy acid, make the epoxide, ozonolysis, consider the workup if it's oxidative, change those carbons that are in the double bond from CH to COH. So split the double bond, put oxygens in their place, and replace the OHs with OHs if it's oxidative. Keep the CH bonds if it's reductive workup. And the last one we briefly discussed in the first presentation was the radical reaction. If HBr is used specifically with peroxides, we have an anti-Markovnikov addition of H and Br with no stereoselectivity. And it was our one radical reaction. I would highly recommend, if you're looking at alkene reactions, that you create your own star diagram or spider diagram so that you can help memorize very quickly the regio and stereochemical notes for those particular reactions of an alkene. Developing your own chart, writing your own notes down regarding regio and stereochemistry just helps you memorize where to go as you draw a product. Bye-bye.